Welcome. This is the regression analysis course. My name is Nicoleta Serban. I'm an associate professor in the Stewart School of Industry and System Engineering. The lecture is multiple linear regression, and I will return to the SAT example and focus on model fit. So far, we studied the estimation and statistical inference for the SAT example. In order to reliably make inference on the regression coefficients and on the regression line, we need to also ensure the model fit. In this lesson, we'll perform the residual analysis for this example. We can obtain the residuals as provided on the first R command line, in which the model object reduced line followed by the $sign and then specifying the residuals. The next command line obtains the cooked distances used to identify outliers. The set of plots of interest are the scatter plot of the response variable or fitted values versus residuals along with the zero line. There's also the scatter plot of the quantitative predicting variables versus the residuals, the histogram and normal probability plot, and last, the plot of the Cook distance. To review, we evaluate the assumptions of constant variance and uncorrelated errors by plotting the response or fitted values versus residuals. To evaluate the assumption of linearity, we plot the predicting variables versus the residuals. In all these plots, in all these scatter plots, we seek a random pattern around the zero line. To evaluate normality, we use the histogram and the normal probability plot. And last, for evaluating outliers, we use the Cook distance plot. Let's discuss these assumptions using these plots on the next slide. In the plot of the residuals versus SAT scores, there is a clustering in the residuals, with the grouping into two clusters, possibly an indication of correlation. It is possible that the controlling factors may not have control for the bias selection fully using the linear model. Moreover, the plot of takers, or the percentage of students tested versus residuals, has higher residuals on the edges and low residuals in the center. This is an indication of nonlinearity with respect to this predictor. Thus, we will need to transform this predictor. Note that the separation in the residuals in the first plot could be a product of the fact that there is a nonlinear relationship with respect to takers, with respect to this predictor, which is a controlling factor for the bias selection. The QQ plot indicates that the residuals in our regression model have heavy tails. On both the negative and positive side, observed sample quantiles, the quantiles of the residuals, are larger than theoretical quantiles. The histogram points to this as well. The residuals do not show outliers as we might have expected. Recall that Alaska had a large expenditure, but it does not show as being an outlier or influential point based on this model. Next, we're going to transform the predicting variable takers, and we will redo the analysis using this transformation. So now we're going to look at the linear model where we replace takers with log of takers, and this is the output of this model. To note that while in the model without the transformation, takers was not statistically significantly associated to the SAT score, given all other predictors variables in the model, now with the transformation, it is statistically significant at the significance level of 0.05. The p-value is 0.02. However, now the predicting variable rank is not statistically significant anymore as compared to the model without transformation. The R-square improves slightly from 87.8% to 89%. The standard deviation of the error term decreases slightly also. The linearity assumption does hold now for the two predicting variables. So now we can look at the residual, the plot of the log of percent of students tested versus residuals, and we don't see the pattern that from the model without transformation anymore. However, we still see some clustering in the residuals versus ACT scores, although it's less so than for the model without transformation. The distribution of the residuals is still heavy-tailed. Now, we see one Cook distance standing out, and that is the value corresponding to Alaska. So now for this model, with transformation, we see with the outlier, the values for the Alaska is an influential point. And the reason is that the predicting variable expenditure now has it's strongly associated to the SAT score because the p-value is small. So we see a change also in the statistical significance for expenditure. So let's review here. The transformation has improved the linearity assumption. We still have heavy-tailed residuals, and the Cook distance shows that Alaska is an outlier, an influential point for the model. You would need to study this outlier further for a more comprehensive analysis. Let's now review the findings based on this analysis. Given all other predictors in the model, percent of students taking SAT from public school and family income of test takers are not statistically significantly associated to SAT score. Given all other predictors in a model with 100,000 increase in expenditure on secondary school results, we see only a 2.56 point increase in the SAT score. In contrast, given all other predictors in the model, one additional year that test takers had in social sciences, natural sciences, and humanities leads to 17.2 points increase in the SAT score. The predictors in the model explain close to 90% of the variability in the SAT score. We find that relationship between state average SAT score and the percentage of students taking SAT to be nonlinear for this example. Ranking changes significantly after controlling for the bias selection factors. For example, Connecticut moves up to be the first from 35th, Massachusetts to 4th from 41st, and New York to 5th from 36th. To summarize, in this lesson, we performed an analysis of the model fit that will provide us more insights about the reliability of the statistical inference of our findings. I will also summarize the findings based on the analysis we performed for the performance of SAT across states. Thank you.